Okay, we will try this example. We will try to work out this sample problem. So for number 1, a 1 meter pipe or a 1 meter diameter new cast iron pipe is 845 meters long and has a head loss of 1.11 meters. Find the discharge capacity of water for this pipe using Manning's formula. So first, you have to list all the given. So we have here the diameter is 1 meters. Then you have the length of the pipe is 845 meters long. Head loss is equal to 1.11 meters. Then you have to find the discharge Q. Okay. In finding the discharge Q using Manning's equation, you have 1 over N, area R 2/3, S 1/2. Okay. Looking back to the formula, we need the value of N and we need also the value of S. Because area and the hydraulic radius will be determined because of we have already the diameter, no? So we already that one. So we can use that one. Then we will assume that the pipe is flowing full. So that's why the area is just equal to pi d squared over 4. That is the area of the circle, because we are assuming that the pipe is flowing full. So we have that one. For N value, we can determine this one by looking at the type of material of the pipe. So since in this problem, we need, it is mentioned that the pipe is a new cast iron pipe. So we can get the value of the roughness coefficient for a new cast iron pipe. So there are tables, no, for that value. So for a new cast iron pipe, your N is 0.013. Another is your slope. So since the given is head loss, you can determine the slope because the length is also given. So slope is just equal to, slope is just equal to head loss over L. Or sometimes we can say that is rise over run. So if we have this one, this is the slope, this is head loss, and this is the length. Okay? So slope is just equal to HL over L. Okay, substituting all of these values, this one, okay, you can determine the velocity. So try to compute this one. If it is equal to 1.106 meter per second. So that is the velocity. Okay, kindly compute that one. So 1.106. Substituting the value of velocity to the equation, since our equation, the general equation for the discharge is just equal to area times velocity. The formula velocity can be determined what type of formula we are going to use. If we use Darcy-Weisbach equation, so we will use F. Okay, the friction factor. If friction factor is given, you will use in getting the velocity using Darcy-Weisbach equation. If the value is C, no? If C value is given, so we will use the Hazen-Williams equation in getting the velocity. If the value of N is given, okay, so Manning's equation will be used. There is also for a new cast iron pipe, you can determine also F, no? For new cast iron pipe, you can determine the value of F because the E here, the roughness coefficient is given. So once you have your E, then you have this one, E over D, then once you have your velocity and your Reynolds number, so you can get the friction factor. Okay? But here, it is emphasized that we will use Manning's formula. So that's why we use Manning's formula in getting the Q. If it is not emphasized, okay, emphasized that we are going to use Manning's formula, so it means that you can determine also the value. You can it depends upon the given, no? Sometimes it is not emphasized in the problem. It's not emphasized, but that's why I let you write all the given so that you will know what is the applicable formula we are going to use. Okay, so here in our problem, we will use the Manning's equation. Especially the head loss is also given in order for you to get the slope. Okay, so the answer for number 1, Q is 0.8. Okay, 869. So I advise you to box your final answer, or you have to encircle your final answer in order for me to easily check your final answer. Okay, for number 2, you have here a 320 mm diameter pipe. Okay, F is 0.025, 140 meters long, runs from a reservoir to another. Both ends of the pipe being underwater. That is in figure here 2.12. So this is your figure 2.11. Okay, the intake is square edge. So here we need to determine the type of the entrance. So it is a square edge intake. Then the difference between the water surface levels of the two reservoirs is 36 meters. Find the flow and the pressure in the pipe at a point 95 meters from the intake. So we are going to get, so if this is your X and that is 95 meters from the intake, okay, it is 95, 95 meters from the intake. So here, if that is the distance, where the elevation is 39 meters lower than the surface of the water from the upper reservoir. So here your delta Z is 39 meters. Okay, so we are going to find the flow or find the Q. So for letter A, you have to find the Q. So find the Q. For letter B, okay, for letter B, you are going to find the pressure. Okay, find the pressure. Okay, from the figure, I hope you understand this. Okay, so let's try. I hope you can directly see where these equations from. Okay, if this is our equation 1, if that is your reservoir 1 and this is your reservoir 2, we will we will get the energy equation between 1 and 2. But here we have to consider the losses. So considering head losses. So what are the type of losses? Head losses, we have two types. The friction loss, that is major losses, and the minor losses. Okay? So in this case, you have P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G plus summation of head loss. Okay, where head loss is equal to, okay, what is the head loss? Head loss is just equal to the head loss due to friction plus the head loss due to, okay, the minor losses. So what are the minor losses? The head loss at the entrance. Since the discharge is also submerged, okay, plus head loss at the discharge. Okay? So the formula for the friction factor, friction loss is equal to F. We will use Darcy FL V squared over 2G. Okay? Plus head loss at the entrance. Okay? V squared over 2G plus head loss at the discharge is equal to V squared over 2G. The head loss at the entrance is, okay, the head loss at the discharge is KD, that is the coefficient of discharge, times V squared over 2G. So try to look at what are the common. So the common is, okay, for head loss, okay, for head loss, okay, common is, okay, you have V squared over 2G, okay, times FL over, okay, times, okay, FL V squared. Okay, so you have FL plus, okay, plus KE plus, okay, FL plus KE plus KD, KE and KD. So you have there V squared over 2G, okay, times F. What is the value of F? So you have 0.0, okay, 0.5, okay, 0.5 plus, okay, what is the value of KE? Sorry. F is 0.025, 0.025, okay, times, okay, there's D, no, here, okay, times, what is L? L is 140, so times 140 over D. D is 0.32 meters. Okay. 0.32 meters, okay, plus KE. KE is equal to, what is the value of KE? That is at the entrance. So we have two. We have 0.8 and 0.5. So you have, okay, what is the value of the KE? We have two, the 0.5 and the 0.8. Okay, it's not here. Okay, here. So square edge. Okay. So you have because you have a square edge. When you say square edge, so it is flush, no? Another term for a square edge is a flush entrance. So you have here, no? That one. So your KE is 0.5. So you have to remember that one. Then we have to substitute it here. Okay, that is 0.5. 0.5. So 0.5. Then the coefficient of discharge is equal to 1. Okay? So this is the formula of your head loss, where head loss is 36 meters. So I hope you understand this. So this is the derivation of this equation. So what will happen? Okay, your velocity now is 0.754 meter per second, and your discharge is 0.606 meter cube per second. Okay, another one, we are going to determine the pressure. Okay, so it is said that we are going to determine the pressure in the pipe at 0.95. So you can just change the length. Okay, the same formula of this. Okay, no, but we don't have the discharge anymore. Okay, because if we are going to draw for letter B, it can be like this. Okay, so like that. So this will be X is 95 meters, somewhere from the entrance. So here, that is your Q. Okay, so what you have here for the head loss is just equal to head loss at the entrance plus head loss of the pipe. So that is only head loss we got, no? So here your entrance is, no? Okay, that is the entrance is KE times B squared over 2G. Then so you have 0.5. Then HF is equal to FL V squared over 2G. So upon derivation, so you have here head loss is equal to Okay, so KE V squared over 2G plus FL V squared over D 2G. So you have V squared over 2G is equal to KE, okay, plus FL over D. Okay, so this will be now the computation. So you have to substitute the value, then you can get the head loss. Okay, what is the value of the head loss? So head loss will be, okay, we will try to compute if it is the value of the head loss. Okay, so you have 0.5 plus 0.025 times 95 divided by 0.32 okay, times 2.89. Oh, it's syntax error. Okay, again. We will try again. So, the answer is, what is the answer? Okay, again, 0.025 times 95 divided by 0.32. Okay, plus 0.5 times 2.89. So the answer is 22 point. So your head loss here, okay, your head loss is equal to 22 point, okay, 22.894. So, okay, 22.894 meters. But here, the book uses 22.9. Or in our exam, we have to round off up to 3 decimal places to make it uniform, okay? So here, we have here head loss. So head loss is 22.894. So this is now the value of the head loss. Then go back to the equation again. Okay, so go back to the equation. Okay, I'll try to go back to the equation. Okay, I have to delete this. Okay, go back to the equation. So for section, this will be the equation. This is your section 1 and this is your section 2. So you have P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G plus head loss. Okay, head loss. So you have P1 that is equal to 0 since it is exposed to atmospheric pressure. P2 is also 0 because it is also exposed to atmospheric pressure. And Z1, okay, the elevation Z1 minus Z2, okay, Z1 minus Z2 is equal to, okay, since here the velocity, this one, is also equal to 0 because it is assumed that the velocity at the reservoir is negligible. So what remains is only Z1 minus Z2 is equal to V2 squared over 2G because inside the pipe there is a velocity. So here, no, sorry. There is a Yeah, because that is within the pipe. Sorry, again, I have to repeat again. So P2 is not exposed to atmospheric pressure. Sorry. Okay. P2 is not exposed to atmospheric pressure because it's just, no? This is not, okay. This is not exposed to atmospheric pressure because it is somewhere, no? Somewhere here, somewhere in the pipe. So there is a pressure there. So what you have is only, so the equation will be now Z1 minus Z2 is equal to P2 over gamma, okay, plus V2 squared over 2G. So you have here 39 is equal to, okay, plus head loss. So what you have 39, okay, 39 minus head loss. So 39 minus head loss, your head loss here, there is, how much is the head loss? Okay, you have 22, okay, the book is supposed to be 22.894, so say, because we will use the book, no? The values used here. So say 22.9, okay, meters. So you have 39 minus 22.9 is equal to P2 over gamma plus, okay, plus V squared over 2G. Okay, so from there, I have to erase this. Okay, so you have here 39.229, 22.9. Okay, 39 minus 22.9 is equal to P2 over gamma plus V2 squared over 2G. Since we are going to find the pressure at point 2, so what we have is 39 minus 22.9 minus V2 squared over 2G. Okay, so this will be, okay, this will be the answer. No? We have 13.29 meters. So multiply the unit weight to 13.29. So the pressure at section 2 is 130.41 kPa. Okay? So I hope you understand the problem. Okay? So here for number 3, two pipes, each 300 meters long, are connected in series. The flow of water through the pipes is 100 liters per second with a total friction loss of 15 meters. If one pipe has a diameter of 300 mm, what is the diameter of the other pipe? Neglect the minor losses. So, okay, so the friction factor is 0.02 for both pipes. Okay, we will try this one. Okay, so here again we will try to draw we will try to illustrate the problem. So you have here, you have two pipes. Okay, you have two pipes. Okay, the length is equal to 300 meters long. Okay, the flow, it is connected in series. So it is said, it is assumed if the diameter of the other pipe is 300 meters, 300 mm, sorry. Okay. So what will be the diameter of the other pipe? So we don't know, no? We don't know if the diameter is greater or if the diameter is lesser. So we don't know. As long as their length is 300 meters. Okay? We don't know what is the diameter of this pipe. So we let this one up D1. This is D1 and we let this one as D2. Okay? So here, the Q here are constant. Okay? So using continuity equation, Q1 is equal to Q2. So we'll let this one as pipe 1 and this is our pipe 2. So Q is given and that is 0.15 meter cube per second. Okay, so since the pipe is in series, so you are going to add, no? To add the head loss. Unlike for parallel pipes, the head loss are equal. Since friction factor is also given, so we will use Darcy-Weisbach equation in determining the head loss of each pipe. Okay, so here, let's see, this will be your equation 1, and this will be your, okay, this will be your head loss for pipe 1. Okay, pipe 1. And this is your head loss for pipe 2. Okay, since the problem there, we have to neglect minor losses. So that's why our head loss is only due to friction. And it is hard for us also to determine, if we include the minor losses, it's hard for us to determine whether the pipe is from smaller pipe to larger pipe. So there is a enlargement of the pipe. So it means that D2 is greater than D1, or if D1, if there is a sudden expansion, as a sudden contraction of the pipe, so it means if D1 is greater than the pipe 2, or D1 is greater than D2. So we don't know, okay? So that's why we have only to neglect the head loss. So since head loss there is equal to 15, so you have here 15. Okay, we can compute now the diameter. So diameter is 255 mm. So it means when we neglect the minor losses, the diameter is 255. So there is a sudden contraction of the pipe, producing a Q which is equal to 0.15 cubic meter per second. Okay, so you have to remember, if we neglect the minor losses or we include the minor losses. But here in this topic, we have to consider all, as long as it is stated in the problem that we are going to neglect the minor losses. Okay? For number 4, water flow at rate of 200 liters per second, okay, through 120 meters horizontal pipe having a diameter of 300 mm. Okay, 300 mm. If the pressure difference between the endpoints is 280 mm of mercury, determine the friction factor. Okay, so here, so it is said that you just have a horizontal pipe. Okay, so you have here pipe 1 and pipe 2. Okay, it is said that for a horizontal pipe, the head loss between the points is equal to the difference in pressure head. So the head loss between the points is equal to the pressure head. So you have, okay, so you have head loss is just equal to the pressure head, the difference of the pressure head. Okay, that's why we have this one. And that is in mercury. So we're going to multiply, no, the specific weight. No, okay. We're going to multiply the height of the mercury to the specific gravity, no? The specific gravity in order to make it in water. So if you remember in your fluid mechanics, it is said that the pressure of the fluid having the same elevation or along horizontal line. For example, if this is your fluid 1, so we can have P1 and this is also your P2, that is your fluid 2. Okay, so to get, no, they have the same pressure. You have gamma 1 H1 for fluid 1 and gamma 2, okay, gamma 2 H2 for fluid 2. Okay, so since P1 is equal to P2, so you have gamma 1 H1 is equal to gamma 2 H2. Okay, so if you are going to get the height of fluid 1, which is equivalent height of fluid 2, so you have gamma 2 H2 over H1. Okay, from that, your H1, your gamma 2 is equal to specific gravity of fluid 2 times specific gravity of water times H2 over specific gravity of fluid 1, gamma of water, H1. So, cancel out this one. So, sorry. Okay, sorry. Okay, so what you have is equal to, so the equivalent height, no, of fluid 1 to the, or the equivalent height of fluid 2 to fluid 1 is equal to the specific gravity of fluid 2 times the head of fluid 2. Okay? So if H1 is equal to head of water, so you can say that just to get the equivalent height of mercury, okay, the equivalent height of the mercury to water is multiplied by the specific gravity of mercury times the fluid which or times the head of the fluid, which is the mercury, no? So that's why we are going to multiply 0.28 times 13.6 to get the equivalent height of water, no? So that equivalent height of 0.28 mmHg is equal to 3.808 meters of water. So that's the derivation of the formula. Then, okay, so from the equation, we have Darcy-Weisbach equation. Substitute it to the formula, then you can have the answer. F is equal to 0.0233. Okay? So I hope you understand. Okay, for this, number 5, what commercial pipe size of new cast iron pipe shall be used to carry a 4,490 gallons per minute with a head loss of 10.56 feet per mile? Assume F is 0.019. So, I'll try to list you the given, okay? So, Q is equal to 4,490 gallons per minute. Then head loss is 10.56 feet per mile. Okay, 10.56. Then F is 0.019. So the type of this is the new cast iron pipe. Okay, then you are going to find the diameter. Okay, so for new cast iron pipe, since F is given, so we will use Darcy-Weisbach equation again. So we have this one. Then we need the value of this new cast iron pipe is E, not for Manning's roughness coefficient, that is N. So the E for a new cast iron pipe okay, I guess no need to determine the E because F is already given, that is 0.019. Unless if the friction factor is not given, you need to identify the new cast iron pipe and to determine the E, no? To identify the type of material. Oh, okay, that is new cast iron pipe. Okay, so here you convert Q into cubic meter per second. So you have your units must be consistent. So if you like metric, it's okay. If you like English, it is okay. But you have to remember that this formula, you can use this. No, you can use that for SI. Metric or SI, is that okay, metric formula. I guess you can use this also in English, no? Because if we are going to derive, no, HF is equal to FL V squared over D2G. So you don't have the units there. What you have is only Q. You have Q squared over A squared over D2G. So you have FL, you have Q squared, and that is D2G pi over 4 D squared. Okay, so I guess it's okay, no, to use this in English. Okay, so if you use English, your Q must be in English and your length must be also in English. But yeah, you have to be consistent with your units. Okay, so upon derivation or upon the since you already have the value, substitute values to the equation. So your value for D is equal to 0.0576 meter per second or 576 mm. Okay, so I hope you understand the principle behind of this subject, of this chapter, no? Chapter 1, the review of fluid fundamentals. And here, I like you also to answer this one. Okay? Again, I like you to answer this one. I hope you can answer this. Okay? This will be your assignment number 2. Okay? Try to check the figure. Is it okay if it is clear? Okay? Then, this one. Okay? So, you also have number 8. And this will be the these are the references of this chapter 1. Okay? So, you can search the book and the internet. Okay, the internet sources.